How many galaxies are there in the universe? It is believed that no one can provide an exact answer, as the number of galaxies in the universe is so vast that it is beyond human imagination. Therefore, we can only estimate the approximate number using certain methods. For example, by photographing a small section of the sky and counting the number of galaxies within it, we can then extrapolate to estimate the total number of galaxies across the entire sky. This gives us a rough idea of how many galaxies exist in the universe. Between September 2003 and January 2004, astronomers used the Hubble Space Telescope to capture a groundbreaking image known as the Hubble Ultra-Deep Field. This image revealed some of the deepest regions of our universe and became a significant milestone in the history of astronomy. The Hubble Space Telescope was pointed at one of the darkest patches of the sky, an area only about 1/10 the size of the full moon. Over approximately 11 days, the telescope took 800 exposures to produce this image. Surprisingly, this seemingly empty region of the sky was actually filled with distant galaxies, containing at least 10,000 galaxies, each of which in turn contains billions of stars. The Hubble Ultra-Deep Field fundamentally changed our understanding of the universe. It showed that even the darkest, seemingly empty regions of the sky are teeming with countless galaxies and stars. Based on the observations from the Hubble Ultra-Deep Field, astronomers estimate that if we were to photograph the entire sky, the observable universe alone would contain at least 2 trillion galaxies. This number is almost unimaginable. However, even though there are so many galaxies in the universe, this estimate might only be the tip of the iceberg. It is important to note that these 2 trillion galaxies are only within the observable universe, which spans about 93 billion light-years. Beyond this range, objects exist whose light has not yet reached Earth, making them currently unobservable. As human technology continues to advance, we may discover even more galaxies in the future, further expanding our understanding of the universe. However, the total number of galaxies in the entire universe may forever remain unknown to us, as the scale of the universe is so vast that it exceeds human comprehension. Temperature measures how hot or cold an object or system is, essentially reflecting the intensity of molecular thermal motion within it. But have you ever wondered what the highest possible temperature in the universe could be, or how low the lowest temperature might go? Theoretically, temperature has no upper limit. It can reach any extreme height because, at the microscopic level, temperature is determined by the intensity of particle motion. The faster the particles move, the higher the temperature. This motion can intensify as energy increases. Within the framework of special relativity, although particles with mass cannot reach the speed of light, their kinetic energy can increase indefinitely. As a particle's speed approaches the speed of light, its kinetic energy also approaches infinity, and thus the temperature approaches an infinitely high value. However, in the universe, temperature has never reached infinity. This is purely theoretical. The highest known temperature in the universe occurred approximately 13.8 billion years ago, at the very moment of the birth of the universe, the first Planck time after the Big Bang. This temperature is known as the Planck temperature. Based on modern cosmological models, scientists estimate that at the moment of the Big Bang, the temperature reached about 1.4 times 10 to the power of 32 degrees Celsius. This temperature, none of the matter we know today, atoms or fundamental particles, existed. Moreover, the 4 known fundamental forces were unified. As the universe expanded and cooled, such extreme temperatures have never been observed again. Now let's discuss the lower limit of temperature. While temperature has no upper limit, it does have a theoretical lower limit, absolute zero, which is minus 273.15 degrees Celsius. However, absolute zero is unattainable. As mentioned earlier, the temperature of an object is determined by the thermal motion of its internal particles. The more intense the motion, the greater the average kinetic energy, and thus the higher the temperature. Conversely, as particle motion approaches a standstill, the temperature approaches absolute zero. In quantum mechanics, all microscopic particles that make up the universe are governed by inherent uncertainty. Their position and momentum are constantly fluctuating and never come to a complete stop. This means absolute stillness is impossible in the quantum realm. If particles were to stop, their position and momentum would become precisely defined, violating the uncertainty principle of quantum mechanics. Furthermore, the third law of thermodynamics states that absolute zero can never be reached. It can only be approached infinitely. This is because any space must contain some energy and heat. As a result, absolute zero remains forever out of reach. The Andromeda Galaxy, located approximately 2.54 million light-years away, is the closest large galaxy to us. Like the Milky Way, it is part of the local group of galaxies and holds the title of the largest member within this group. The Milky Way ranks second, followed by about 50 smaller galaxies and dwarf galaxies. With a diameter of roughly 220,000 light-years, the Andromeda Galaxy is 1.6 times larger than the Milky Way and is home to over 1 trillion stars. You might have heard that the Andromeda Galaxy is currently on a collision course with the Milky Way. In about 3.75 billion years, the two galaxies are expected to merge, forming a colossal new galaxy. While this monumental event lies in the distant future, recent astronomical observations reveal that the Andromeda Galaxy and the Milky Way have already begun interacting. Specifically, their halos, cloud-like structures of diffuse material surrounding the galaxies, are colliding. The Andromeda Galaxy's halo extends an astonishing 2 million light-years, and the Milky Way's halo is similarly expansive. This means the diffuse material of both galaxies is already mingling, though the main collision between their central regions won't occur for another 3.75 billion years. This raises an intriguing question. In the early 1920s, astronomer Edwin Hubble observed that most galaxies in the universe exhibit redshift, indicating they are moving away from us. This discovery led to the conclusion that the universe is expanding. So, if the universe is expanding, why is the Andromeda Galaxy moving closer to us? While the universe is indeed expanding, causing distant galaxies to drift apart, astronomers have detected a blue shift in the Andromeda Galaxy's spectrum. Blue shift occurs due to the Doppler effect, where the wavelength of light shortens as an object moves closer, shifting the color toward the blue end of the spectrum. Conversely, redshift happens when an object moves away, stretching the wavelength toward the red end. By analyzing this blue shift, scientists determined that the Andromeda Galaxy is approaching us. The explanation is straightforward. The Andromeda Galaxy is relatively close, at just 2.45 million light-years away. At this distance, the expansion of the universe is not strong enough to overcome the gravitational pull between the Milky Way and Andromeda. In other words, their mutual gravitational attraction outweighs the effects of cosmic expansion. As a result, the Andromeda Galaxy is hurtling toward us at a speed of 120 kilometers per second. In approximately 3.75 billion years, the central regions of the two galaxies will begin to collide. However, galactic collisions are not catastrophic events. They unfold as slow, gradual processes. The dramatic visuals we see today are based on computer simulations created by astronomers to model the collision. During the collision, stars will not physically collide but will instead pass by each other. Initially, the interaction will trigger the formation of numerous new stars. Afterward, the two galaxies will separate and then draw closer again, leading to a second interaction about 5 billion years later. Eventually, the cores of the two galaxies will merge, forming a new massive elliptical galaxy. This merger will stand as the most spectacular astronomical event in the history of the Milky Way. Black holes can be said to be among the most mysterious and terrifying celestial objects in the universe. Their existence has almost disrupted our understanding of the universe, as their nature and behavior not only challenge humanity's comprehension of natural laws, but also bring forth numerous unsolved mysteries about space-time and gravity. So, just how terrifying are black holes, and where does their horror truly lie? One of the most fearsome characteristics of black holes is their immense gravitational pull, so powerful that it can warp the surrounding space-time. This force ensures that any object venturing too close is inevitably consumed. The event horizon, the black hole's most enigmatic boundary, marks the critical point beyond which nothing, not even light, can escape. All observable events occur outside the event horizon. Inside it, the escape velocity exceeds the speed of light, rendering everything within invisible to external observers. In other words, once matter crosses this boundary, it is lost forever, taking all information with it. According to Einstein's general theory of relativity, the center of a black hole may harbor a singularity, a point of infinite spacetime curvature. At this singularity, all known physical laws break down, leaving scientists unable to describe its inner workings with current theories. This incomprehensible and indescribable state only deepens the enigma of black holes. In addition to distorting space, black holes also warp time. When an object approaches a black hole, it experiences time dilation. Time slows dramatically near the event horizon compared to distant regions. Theoretically, if a human could survive near a black hole, they would witness the outside world aging rapidly while their own time crawls. Black holes also unleash terrifying energy through accretion disks and relativistic jets. As matter spirals toward a black hole, it forms a rapidly rotating accretion disk outside the event horizon. Friction and compression within the disk generate extreme temperatures and intense radiation. Some black holes even eject high-speed particle jets from their poles, stretching thousands of light years and impacting surrounding galaxies with colossal energy. So, how do these monstrous objects form? Black holes fall into two main categories: stellar black holes and supermassive black holes. Stellar black holes form from the remnants of massive stars. When such a star exhausts its fuel, it undergoes a supernova explosion. If the remaining core exceeds about 3.2 times the mass of the Sun, gravity crushes it further, collapsing it into a black hole. Supermassive black holes, found at the centers of galaxies, are millions to billions of times more massive than the Sun. Their origins remain one of astronomy's greatest mysteries. While some theories suggest they grow by merging with smaller black holes, others propose they formed directly from collapsing gas clouds in the early universe, long before stars and galaxies took shape. Despite these theories, the exact mechanisms remain unproven. Yet, as scientists continue to study black holes, future breakthroughs promise to unravel more of their profound mysteries. In our previous discussion, we talked about how black holes are among the most mysterious and extreme celestial objects in the universe. They are typically formed from the collapse of massive stars. When a star reaches the end of its life, its fuel is exhausted, and it can no longer sustain nuclear fusion to release energy. This disrupts the gravitational equilibrium of the star, leading to a catastrophic supernova explosion. The core that remains after the explosion is called a stellar remnant. If this remnant exceeds 3.2 times the mass of the Sun, it will further collapse to form a black hole. Black holes possess an incredibly strong gravitational pull. Around them, space-time is distorted to an extreme degree, so much so that even light cannot escape once it enters their gravitational influence. This is why we cannot directly observe black holes, and must rely on indirect methods to detect their presence. It's easy to imagine just how extreme these objects are. Now, considering such an extreme object, what would happen if one black hole encountered another? When two black holes approach each other, they first begin to spiral closer together under the influence of their mutual gravitational pull. As the distance between them decreases, their rotational speed increases dramatically. This spiraling motion causes intense distortions in spacetime, generating gravitational waves. As the two black holes draw even closer, their event horizons eventually touch, marking the beginning of the collision. This is an incredibly brief and violent moment. Within milliseconds, the two black holes merge into a single, larger black hole. During this merger, an enormous amount of energy is released in the form of gravitational waves, equivalent to the conversion of 8 times the mass of the Sun into pure energy. After the two black holes merge, the newly formed black hole gradually stabilizes, bringing an end to this terrifying cosmic dance. The result is a larger, more massive black hole, a testament to the extreme forces at play in the universe. How was the Earth formed? The most widely accepted theory today is that about 4.6 billion years ago, the Earth was formed from the remnants of material surrounding the primordial Sun. Through continuous collisions and accumulation, these materials eventually coalesced to form the early Earth. But what exactly was this process like? Our story begins with a vast cloud of interstellar dust and gas, known as the solar nebula. This nebula was once quietly floating in space until one day, it experienced a disturbance that created a high-density region. Under its own gravitational force, the nebula collapsed, forming a rotating disk-like structure. As more material gathered at the center of the disk, the temperature and pressure increased, eventually triggering thermonuclear reactions. This is how our Sun was born. After the Sun formed, the remaining dust and gas continued to orbit around it, gradually condensing into tiny particles. Over time, these particles collided and adhered to each other, growing larger through countless impacts until the Earth was formed. During this period, the Earth resembled a hellish landscape, with its surface covered by molten lava oceans. Shortly after the primordial Earth formed, around 4.5 billion years ago, a Mars-sized celestial body named Theia collided with Earth in a massive impact. The debris from this collision formed a ring around the Earth, which eventually coalesced under gravity to form the Moon. This collision not only created the Moon, but also gave the Earth its axial tilt, which played a crucial role in stabilizing the planet's climate over time. After enduring intense collisions and high temperatures in its early stages, the Earth's surface began to cool. However, this cooling was accompanied by frequent volcanic activity, which released large amounts of gas. These gases gradually rose, forming the Earth's early atmosphere. Around 4 billion years ago, the Earth entered a period known as the Late Heavy Bombardment, during which numerous asteroids and comets continuously struck the planet. Comets also brought significant amounts of water and organic materials. As the Earth's environment gradually stabilized, oceans and an atmosphere formed, creating the necessary conditions for life to emerge. Scientists believe that around 3.8 billion years ago, the earliest single-celled life forms emerged from hydrothermal vents on the ocean floor. Over time, these simple organisms evolved into more complex life forms, eventually giving rise to the vibrant and diverse world we see today. In the universe, nothing is absolutely at rest. From the smallest atomic structures to the largest galactic scales, everything is in perpetual motion. For example, we on Earth may not perceive our own movement, but in reality, Earth is continuously orbiting the Sun at a speed of 30 kilometers per second. Meanwhile, the Sun itself is moving around the center of the Milky Way at a speed of 230 kilometers per second, completing one orbit approximately every 230 million years. Similarly, our Milky Way galaxy is also moving toward a specific destination, known as the mysterious Great Attractor. In the 1970s, astronomers observed the motion of galaxies and discovered that the Milky Way, along with numerous surrounding galaxies, was being pulled by a tremendous gravitational force toward a particular direction. At the time, scientists did not know the exact location of the Great Attractor. This general direction lies within the Milky Way's zone of avoidance, an area obscured by galactic dust and stars, which hindered observations. It wasn't until the advent of X-ray telescopes, capable of penetrating this dust, that the Great Attractor was identified in the direction of the constellations Hydra and Centaurus. So, what exactly is the Great Attractor? It is not a single celestial object, but rather a massive region within the Laniakea supercluster. This area contains dense clusters of galaxies and galaxy groups, along with a significant amount of dark matter, creating a massive gravitational anomaly. The gravitational pull of the Great Attractor is so strong that it influences not only our Milky Way, but also galaxies hundreds of millions of light-years away. Currently, our Milky Way is moving toward the Great Attractor at a speed of about 600 kilometers per second. Despite its immense gravitational influence, the Great Attractor will not forever dominate our galaxy. The universe is expanding at an accelerating rate, particularly due to the effects of dark energy, causing the distances between galaxies to grow over time. This means that the gravitational influence of the Great Attractor will eventually be weakened by the expansion of the universe. In the future, the Milky Way will gradually move away from the Great Attractor until its gravitational effects become negligible. Do alien civilizations exist? The existence of alien civilizations has always been a hotly debated topic. Although we currently lack definitive evidence to prove their existence, given the vast scale of the universe, it is unlikely that Earth is the only planet harboring intelligent life. After all, our solar system is not unique. It is just one of hundreds of billions of stars in the Milky Way, and the Milky Way itself is but a tiny galaxy in the cosmos. Therefore, most scientists believe that humans cannot be the only civilization in the universe. It is only a matter of time before we make contact with them. So, what would happen if an alien civilization were to visit Earth one day? How would it impact humanity? First, the fact that an alien civilization could traverse interstellar distances to reach Earth suggests that their technology has at least solved the challenges of interstellar travel, placing their technological capabilities far beyond ours. Consequences of such contact could unfold in two possible ways. The first scenario is peaceful contact, which is likely the outcome most of us hope for. If an alien civilization were to arrive on Earth peacefully and share their advanced technology, humanity could overcome current limitations in environmental sustainability, resource management, and technological barriers. This could spark an unprecedented technological revolution, profoundly transforming human lifestyles. For instance, if they shared technologies like warp drives or wormhole travel, it would revolutionize our understanding of space and time, making the exploration of the Milky Way and beyond a tangible reality. The second scenario is hostile contact. While there is no evidence to suggest that alien civilizations would harbor ill intentions toward Earth, many science fiction works depict invasions by hostile extraterrestrials. If aliens were to arrive with unfriendly intentions, humanity would face an existential crisis. Even if the entire world united to confront such a threat, it would be nearly impossible to defeat them, as their technological superiority would render human civilization insignificant in comparison. Although the likelihood of contact with an alien civilization remains extremely low for now, if it were to happen, it would be an event that could alter the course of human history. Whether they come as friends or foes, such an encounter would force us to reconsider our place in the universe and rethink our future. The theory of evolution is the process by which biological populations gradually evolve through natural selection. Darwin's On the Origin of Species provides a detailed explanation of this theory. He pointed out that species are not fixed, but evolve into new species through genetic variation and natural selection. The validity of the theory of evolution is currently supported by a wealth of scientific evidence. For example, the fossil record shows changes in organisms over time. Through fossils, scientists can trace the evolutionary history of species. Additionally, genetics reveals genetic similarities between different species through DNA analysis. For instance, humans and chimpanzees share 98% of their genomes, indicating a common ancestor. Comparative anatomy also shows similarities in the anatomical structures of different species. For example, the forelimbs of humans, cats, bats, and whales have very similar bone structures, despite their different functions, suggesting a common ancestor. Since Darwin proposed the theory of evolution in the 19th century, it has become a cornerstone of biology. However, despite being validated by numerous scientists, some people still deny the theory of evolution. For example, they often ask, if humans evolved from monkeys, why don't monkeys evolve into humans now? In fact, the theory of evolution does not claim that humans evolved from monkeys, but rather that humans, monkeys, and other primates share a common ancestor. Around 30 million years ago, the ancestors of humans and monkeys diverged and followed different evolutionary paths. This means that monkeys will never evolve into humans. In fact, the process of biological evolution can be likened to a tree, with each branch representing a different species. The human lineage began with Australopithecus, which evolved into Homo habilis, Homo erectus, and eventually Homo sapiens, the only species in the genus Homo today. Despite the theory of evolution being a mainstream theory, why do some people still reject it? First, cultural and religious factors play a role. Many religions emphasize creationism, the belief that all life was created by a deity in a short period. For believers, accepting the theory of evolution means questioning or even denying their religious doctrines, which can be emotionally and spiritually challenging. Second, differences in education and cognition are significant. Educational background is a key factor influencing whether people accept the theory of evolution. In some regions, insufficient teaching of evolution in the education system or the influence of religious beliefs on educational content prevents some from fully understanding and accepting the theory. This lack of understanding of scientific methods and evidence makes it difficult for them to grasp the scientific basis of evolution. Third, scientific skepticism and misunderstandings persist. While scientific progress often involves questioning and debate, there is no major controversy within the scientific community about the fundamental principles of evolution. Although some details of the theory are still being researched and discussed, some people misinterpret these scientific debates as a rejection of the entire theory, leading them to question its validity. In reality, since the theory of evolution was proposed, scientists have made significant additions and modifications, forming the modern evolutionary synthesis. Fourth, psychological factors also play a role. Psychological research shows that humans tend to be conservative and cling to their beliefs. For example, some people may be influenced by science fiction movies, such as Prometheus, and firmly believe in alternative theories of human origins, such as the idea that humans originated from aliens. They are more inclined to accept views that align with their preconceptions and reject scientific theories. Despite some people denying the theory of evolution, it remains the mainstream scientific theory and is unlikely to change. You can question it and present solid evidence to refute it, but without such evidence, any denial is merely empty talk. A Dyson sphere is a theoretical megastructure designed to harness the energy of a star. It was first proposed by physicist Freeman Dyson in 1960. Dyson envisioned that as a planetary civilization develops, its energy resources would inevitably become limited. Once the civilization reaches a certain level of advancement, the resources of its home planet would be insufficient to support further progress to a higher stage. To maximize energy utilization, such a civilization might construct a massive artificial structure around its star to capture its radiation and convert it into usable energy. This is the concept of a Dyson sphere. There are several possible designs for a Dyson sphere. One is the Dyson shell, a solid shell completely enclosing the star to capture all its radiant energy. However, this design is theoretically challenging to achieve due to the unimaginably vast amount of materials and engineering technology required. Another design is the Dyson swarm, which consists of a large number of densely packed, independent structures orbiting the star. These could be a collection of satellites or solar collectors spaced apart, forming a cloud-like structure around the star. This design is more realistic because it does not require a continuous structure, resembling clouds surrounding Earth. Compared to a complete Dyson shell, a Dyson swarm is more feasible and easier to construct. This structure can also be referred to as a Dyson ring. Additionally, there are other concepts like the Dyson bubble and Dyson net. As for whether Dyson spheres exist in the universe, theoretically, a sufficiently advanced civilization could have the capability to build one. However, this would require at least a Type II civilization on the Kardashev scale. Kardashev's scale categorizes civilizations into 3 levels. Type I civilizations can harness all the energy of their home planet. Type II civilizations can utilize all the energy of their home star, and Type III civilizations can harness the energy of an entire galaxy. From this perspective, a civilization would need to reach at least Type II to build a Dyson sphere around its star and capture stellar energy, as the materials and engineering technology required are far beyond the capabilities of a Type I civilization. Since the proposal of the Dyson sphere theory, scientists searching for extraterrestrial civilizations have attempted to detect signs of such structures by observing the radiation characteristics of stars in the universe. If a star were surrounded by a Dyson sphere, its radiation would exhibit unusual infrared signatures. In 2011, scientists discovered a peculiar star named Tabby's star, located 1,430 light-years away. Its light curve was highly irregular and non-periodic, with brightness dips of up to 22%. Such variations could not be explained by planetary transits. If caused by a solid structure, it would need to be at least half the diameter of the star. This led many scientists to speculate that it might be a Dyson sphere constructed by an alien civilization. However, this remains only a hypothesis, as the star is too distant for us to draw definitive conclusions. Although no conclusive evidence of a Dyson sphere has been found to date, the possibility of their existence in the universe cannot be ruled out. In 1798, the British scientist Henry Cavendish conducted an experiment. Using a device called a torsion balance, he measured the gravitational constant and subsequently calculated that the mass of the Earth is approximately 60 trillion billion tons. Despite the Earth being so massive, when viewed from space, it appears to float effortlessly. In reality, this floating is an illusion. On Earth, we feel objects falling downward due to the force of gravity, which pulls everything toward the surface. However, in space, there is no concept of up, down, left, or right. The Earth is surrounded by empty space, and is primarily influenced by the Sun's gravitational pull. Strictly speaking, the Earth is continuously falling toward the Sun. Yet, we all know the Earth does not crash into the Sun. This is not difficult to understand. As is well known, the Earth is constantly orbiting the Sun at a speed of approximately 107,000 kilometers per hour. This high-speed motion generates centrifugal force, which balances the Sun's gravitational pull. This equilibrium allows the Earth to follow a nearly circular orbit around the Sun. For example, on Earth, if an object is launched at an initial velocity of 7.9 kilometers per second, it will continue to orbit the Earth without falling to the surface, assuming no resistance. This is known as the first cosmic velocity. Similarly, the Earth remains in space without falling into the Sun because the Sun's gravitational force and the Earth's centrifugal force are in balance. This principle applies not only to the Earth, but also to other planets and satellites. These celestial bodies follow the same physical laws, maintaining their respective orbits. If their speeds were to decrease to a point where balance is lost, they would eventually fall into the Sun. However, Einstein's theory of general relativity offers another explanation. According to general relativity, gravity is actually a phenomenon caused by the curvature of spacetime due to mass. The greater the mass, the stronger the curvature of spacetime. The reason the Earth and other celestial bodies appear to float in space without falling into the Sun is that the Sun warps the surrounding spacetime. 3 celestial bodies orbiting the Sun move along this curved spacetime. To visualize this, imagine spacetime as a stretchy fabric. When a massive object is placed on the fabric, it causes the fabric to bend. Smaller objects then move along the curved surface of the fabric. For instance, the Moon orbits the Earth because the Earth warps the surrounding spacetime, causing the Moon to follow the curved path. This phenomenon of spacetime curvature provides a compelling explanation for the orbital motion of celestial bodies. It also deepens our understanding of why the Earth appears to float in space without falling into the Sun. Looking at our Earth from space, it resembles a blue marble suspended against the dark backdrop of the universe. However, until the mid-20th century, people had no clear idea of what Earth truly looked like. Although scientists had long used indirect evidence to prove that Earth is round, it wasn't until the invention of rockets in the mid-20th century that humans finally saw Earth from space and marveled at the beauty of our home. The photo we see here was taken in October 1946. At that time, scientists launched a V-2 rocket to an altitude of 105 kilometers, equipped with a 35mm camera, capturing the first ever images of Earth from space. This marked humanity's first glimpse of Earth from such a perspective. In the decades that followed, as space technology advanced, more and more photos of Earth were taken, revealing its full splendor. For example, the famous photo known as the Blue Marble was taken by astronauts aboard Apollo 17 during their mission, approximately 29,000 kilometers from Earth. This image clearly shows the entire planet, with the edges of Africa lightly covered by clouds. Another iconic photo, taken in 1968 by astronauts on the Apollo spacecraft during a lunar orbit mission, is titled Earthrise. This was the first time humans saw Earth from the Moon, highlighting its profound isolation in the cosmos. While striking, this image pales in comparison to the one you see now. At first glance, this photo may seem unremarkable, but its context is deeply thought-provoking. It was taken by Voyager 1 from a distance of 6.4 billion kilometers away from Earth. The faint, glowing dot in the image is our planet, occupying just 0.12 pixels of the entire photo. Yet this tiny dot contains everything we know. Every person, every joy, and every sorrow occurs on that speck of light. Renowned astronomer Carl Sagan aptly named it the pale blue dot. After seeing these incredible images of Earth, one can't help but reflect on how small and fragile our planet is. Beyond it, we have no other home. On winter nights, when we gaze up at the starry sky, a red star on the shoulder of the Orion constellation always stands out. This star is called Betelgeuse, and it is in the final stages of its life. At any moment, it could unleash a cosmic-level fireworks show. A supernova explosion so spectacular that it would be visible even during the day, shining as brightly as a full moon. When this happens, everyone on Earth will witness the magnificent finale of a star. Betelgeuse is located approximately 640 light-years from Earth. It has a mass more than 16 times that of the Sun, and a volume 700 million times larger. Such an enormous size is one of the hallmarks of a red supergiant star. Back in 2019, astronomers noticed that Betelgeuse's brightness suddenly dimmed, dropping to 36% of its normal luminosity before recovering. This unusual change sparked speculation that it might be on the verge of exploding. However, scientists later discovered that the dimming was caused by the star ejecting a large amount of material from its surface, altering its observed brightness. So, is Betelgeuse really about to explode? According to scientific research, Betelgeuse may not explode imminently, but it is undoubtedly in the final stages of its life. The hydrogen in its core has nearly been exhausted, and it is currently undergoing the fusion of helium into carbon. Once the carbon in its core is depleted, the star's gravitational balance will collapse, leading to a supernova explosion. This explosion could last for months, and its brilliance would be visible even during the day, marking the star's final act of glory. After the supernova explosion, Betelgeuse's core will collapse into a neutron star. If the core's mass is large enough, it might even form a black hole. But will Betelgeuse's explosion affect Earth? Although a supernova explosion can have devastating effects on nearby celestial bodies, Betelgeuse is about 640 light-years away from Earth, posing no threat to us whatsoever. Our Earth was born approximately 4.6 billion years ago, and at its inception, it was an utterly terrifying world, completely unlike the life-filled planet we know today. During that time, Earth was a place of extreme environments and catastrophic events, where no life could survive under such harsh conditions. Today, let's travel back in time to understand just how terrifying the early Earth was. According to scientific research, Earth formed from the collisions of meteorite dust. Under the force of gravity, these meteorites continuously gathered, growing larger like a snowball until they formed a massive planet. In its infancy, Earth resembled a scorching fireball, with extremely high temperatures and a surface covered in molten lava. The atmosphere was filled with toxic gases like carbon dioxide, methane, and ammonia, with no oxygen to breathe. The entire planet was in a constant state of melting and solidifying, with magma erupting frequently, mountains forming and being destroyed repeatedly. But the heat wasn't the only challenge. As Earth formed, it attracted vast amounts of cosmic dust and asteroids, leading to constant surface impacts. Each asteroid collision released enormous amounts of energy, melting the surface again. However, asteroid impacts weren't the most terrifying part. Around 4.5 billion years ago, a Mars-sized planet, known as Theia by scientists, collided violently with the young Earth. This collision was so powerful that it ejected part of Earth's material into space. Over time, these fragments coalesced under gravity to form our Moon. This event not only altered Earth's axial tilt, but also had a significant impact on its future climate. Despite the early Earth's terrifying conditions, over time, the surface gradually cooled. Rocks slowly formed a stable crust, volcanic activity diminished, and water vapor from comets and Earth itself condensed into droplets, falling as rain to form rivers and oceans. Simultaneously, Earth's magnetic field began to form, and the ozone layer started to protect the surface from deadly radiation. Although the emergence of life was still far off, these conditions laid the foundation for future life. Around 3.8 billion years ago, the most primitive single-celled life emerged near hydrothermal vents on the ocean floor. Over billions of years of evolution, this life eventually transformed Earth into the vibrant and thriving home we know today. The Mariana Trench is one of the most mysterious and dangerous places on Earth. Located east of the Mariana Islands in the western Pacific Ocean, it boasts an astonishing depth, making it the deepest oceanic region on the planet. However, exploring this abyss is even more challenging than landing on the Moon. In fact, fewer people have reached the bottom of the Mariana Trench than have set foot on the lunar surface. This extreme environment, filled with challenges and unknowns, has long deterred human exploration. The deepest part of the Mariana Trench is known as the Challenger Deep, reaching a depth of 11,034 meters. If Mount Everest were placed in this trench, its peak would still be submerged under 2 kilometers of water. Pressure here is more than 1,000 times that of atmospheric pressure at sea level, temperatures are near freezing, and the environment is shrouded in absolute darkness. These factors make the trench one of the most inhospitable places on Earth for human survival. The discovery of the Mariana Trench dates back to the late 19th century. However, it wasn't until 1960 that scientists aboard the Trieste successfully reached a depth of 10,916 meters. With advancements in technology, human exploration of the Mariana Trench has become more frequent. In 2012, renowned director James Cameron piloted the deep-sea Challenger solo, becoming the second person to reach the deepest part of the trench. He spent several hours exploring the seabed, capturing valuable footage and collecting geological samples. So, why is exploring the Mariana Trench so difficult? Challenges lie in the immense water pressure, which is more than 1,000 times that of surface atmospheric pressure, combined with perpetual darkness and freezing temperatures. In such extreme conditions, any equipment failure could lead to catastrophic consequences. Even a minor flaw in a submersible could cause it to implode. Additionally, the cold, low-temperature environment significantly increases the likelihood of mechanical failures. Deep-sea exploration also requires complex logistical support, including specialized communication equipment and large support vessels, making the endeavor even more daunting. Despite being an extremely hostile environment, scientists have discovered unique life forms during their explorations of the Mariana Trench. For example, a peculiar species of snailfish was found at a depth of 8,145 meters, and unknown organisms were observed wriggling at depths of 11,000 meters. As technology continues to advance, future deep-sea expeditions are expected to uncover more of Earth's unknown creatures and reveal the secrets hidden in the abyss. This is the largest planet in our solar system in terms of both volume and mass, Jupiter. Its mass is 2.5 times the combined mass of all other planets in the solar system, and its volume is so vast that it could hold 1,300 Earths. As a gas giant, its composition is remarkably similar to that of the Sun, primarily consisting of hydrogen, 75%, and helium, 24%. Given that Jupiter shares the same elements as the Sun, could it become a second star in our solar system? To answer this, we first need to understand the 2 basic conditions required for star formation. 1. Sufficient hydrogen. 2. Enough mass to generate the high temperatures and pressures needed for nuclear fusion in its core. Our Sun originated from a vast cloud of hydrogen gas, a nebula. Due to its enormous mass, gravitational collapse concentrated material at its center, forming a stellar embryo. As this embryo accumulated more matter, rising temperatures and pressures eventually ignited nuclear fusion, transforming it into the radiant star we know today. After the Sun's formation, leftover material coalesced into planets. Lighter gases formed gas giants like Jupiter, while heavier elements formed rocky planets. Jupiter itself formed from these residual gases, but its mass, merely 1/1000th of the Sun's, is far below the minimum threshold for stellar ignition, 0.08 solar masses. To become a star, Jupiter would need to increase its mass by 80 times, enabling its core to reach the pressure and temperature required for hydrogen fusion. Only then could it transform into a luminous, energy-emitting star. In short, while Jupiter shares the Sun's elemental makeup, its current mass relegates it to planetary status. Becoming a star remains a theoretical possibility, but only if it gains an unimaginable amount of additional material. Volcanic eruptions are intense geological phenomena that release vast amounts of magma, ash, gases, and rocky debris, with long-lasting consequences for air, water, land, and climate. Unsurprisingly, they rank among the most destructive natural events on Earth. However, in our solar system, volcanic activity isn't limited to our planet. Some moons, like Jupiter's closest satellite, Io, also experience eruptions. Io isn't just volcanically active, it's the most volcanically violent body in the entire solar system. Its surface is scarred by countless calderas, raging lava flows, and explosive eruptions, making it a prime target for astronomers studying planetary geology. If you could stand on Io's surface, you'd witness a hellish landscape dominated by molten lakes and ceaseless volcanic fury. But why is Io so volcanically hyperactive? The answer lies in Jupiter's immense gravity and tidal forces. Orbiting just 420,000 kilometers from Jupiter, Io is subjected to extreme gravitational tugging. However, this tidal force isn't constant. Io's orbit is elliptical, a shape maintained by its orbital resonance with Europa, Jupiter's second moon. For every one orbit Europa completes, Io completes two, creating a gravitational tug-of-war that locks Io's orbit into an ellipse. As Io swings closer to Jupiter, the planet's gravity intensifies, stretching the moon. As it moves farther away, the pull weakens, allowing Io to relax. This rhythmic stretching and compressing generates intense internal friction, heating Io's core to extreme temperatures. The resulting molten rock and magma are forced upward, fueling its relentless volcanic eruptions. In short, Io's volcanic chaos is powered by Jupiter's gravitational dance, a celestial partnership that turns this tiny moon into a fire-breathing inferno. Why do astronomers believe that even traveling at the speed of light, we cannot reach the edge of the universe? As humanity continues to explore the cosmos, we have gradually come to realize just how vast the universe truly is. Even our own solar system is unimaginably expansive. Suppose we could pilot a spacecraft traveling at the speed of light, 300,000 kilometers per second. Even then, it would take a full year to fly out of the solar system. This is because, based on current observations, the edge of the solar system is the Oort cloud, which lies about 1 light-year away from Earth. Similarly, the closest star system to us, Proxima Centauri, is 4.22 light-years away. Traveling at the speed of light, it would take at least 4 years to reach it. If we attempted to fly out of the Milky Way, it would take tens of thousands of years. And to reach the nearest galaxy, Andromeda, it would take a staggering 2.54 million years. According to current observations, the observable edge of the universe is 46.5 billion light-years away. This means that traveling at the speed of light, it would take 46.5 billion years to reach this region. However, we might never be able to reach these distant galaxies. The universe is not only vast but also expanding. Based on the Hubble constant measured by astronomers, the universe is expanding at a rate of approximately 67 kilometers per second per megaparsec. This means that for every 3.26 million light-years of distance, the expansion speed of the universe increases by 67 kilometers per second. Calculations show that in regions of the universe more than 14.5 billion light-years away from Earth, the expansion speed of the universe exceeds the speed of light. As a result, light from any galaxy beyond 14.5 billion light-years will never reach Earth. This also means that even if we were to pilot a spacecraft at the speed of light, we would eventually be unable to reach certain galaxies, because the expansion of the universe would outpace our speed. The only way to overcome this would be to exceed the speed of light. But Einstein's theory of relativity tells us that no object with mass can ever surpass the speed of light. Question of whether alien civilizations exist in the universe remains unanswered. However, in 1964, Soviet astronomer Nikolai Kardashev proposed a classification system for extraterrestrial civilizations, known as the Kardashev scale. Categorized civilizations into 3 levels. 1. Type 1 civilization. A civilization capable of harnessing all the energy resources of its home planet. 2. Type 2 civilization. A civilization capable of utilizing the total energy output of its host star. 3. Type 3 civilization. A civilization capable of controlling the energy of an entire galaxy. Currently, humanity has not yet reached the level of a Type 1 civilization. Scientists estimate that Earth's civilization is at approximately 0.7 on the Kardashev scale, as we are still transitioning from fossil fuels to renewable energy and have not yet fully harnessed all of Earth's energy resources. So, what would humanity be capable of if we advanced to higher civilization levels? When we reach Type 1 civilization, we will be able to fully utilize all energy resources on Earth. This means we would become the absolute masters of our planet, capable of controlling natural forces such as volcanoes and earthquakes, and even extracting energy directly from Earth's core. Natural disasters would no longer pose a threat to humanity. At the Type 2 civilization level, we would harness the resources of an entire star system, meaning we could fully capture the energy radiated by the Sun. This might be achieved through structures like a Dyson sphere. At this stage, we would have access to nearly limitless energy, the ability to travel freely within the solar system, and even reach neighboring star systems. When we achieve Type 3 civilization, we would be able to harness the energy of an entire galaxy. This would mean not only controlling the energy of stars, but also mastering the manipulation of space-time, and potentially breaking some of the current limitations of physics. At this stage, humanity could travel freely within the galaxy, reaching any star system, and colonizing super-Earths would no longer be a sci-fi dream but a reality. The Sun, the star that provides us with light and heat, is expected to die in about 5 billion years. So what fate will Earth face in the distant future, and where will humanity go? The Sun is a medium-sized star that has been burning for approximately 4.6 billion years since its birth. Currently, its core is undergoing the process of hydrogen fusion into helium. In the future, as the core's hydrogen fuel gradually depletes, nuclear fusion reactions will cease in about 5 billion years. At that point, the core will no longer be able to generate energy to maintain the Sun's gravitational balance, and gravity will take over, causing the core to contract. During this gravitational contraction, the core temperature will rise sharply, triggering stronger fusion reactions, helium fusing into carbon. As this stronger fusion occurs, the radiation pressure from the Sun's core will increase significantly, pushing the outer layers of unconsumed hydrogen and causing the Sun to expand dramatically into a red giant. As a red giant, The Sun's diameter will expand to more than 200 times its current size, engulfing Mercury and Venus. So what will happen to Earth? When the Sun becomes a red giant, the radiation it emits will cause Earth's surface temperature to rise rapidly, leading to the complete evaporation of liquid water and even turning the surface into molten lava. All life on Earth will face extinction. If the Sun expands to Earth's orbit, our planet will also be consumed by the Sun. However, the red giant phase will not last long, perhaps only a few million years. Once helium fusion stops, the Sun's gravitational balance will completely collapse. Outer layers will gradually disperse, forming a planetary nebula, while the core will leave behind a dense white dwarf, continuing to exist at extremely high temperatures with gradually fading light. Faced with such a future, humanity will have no choice but to seek a new home. However, it is believed that in 5 billion years, human technology will have advanced far beyond what we know today. Perhaps by then, humanity will have left the solar system and found a new home somewhere in the universe. The Sun is a high-temperature plasma sphere, and if we could cut it open, we would find it divided into multiple layers. But since we can't directly observe its interior, how do we know about the Sun's internal structure? Although we can't see inside, we can make predictions using certain methods. For example, through helioseismology, scientists observe vibrations on the Sun's surface and use the frequency and speed of these oscillations to infer the density, temperature, and pressure of different regions inside the Sun. Additionally, scientists study neutrinos, which can travel directly through the Sun and reach Earth. By detecting these neutrinos, researchers can analyze and deduce information about the temperature and density of the Sun's core. So, what is the internal structure of the Sun? The Sun's interior is generally divided into 6 layers. First is the core, which is like a massive nuclear reactor with extremely high temperatures and pressures. This causes hydrogen atoms inside to continuously undergo nuclear fusion, releasing enormous amounts of energy. The temperature here exceeds 15 million degrees Celsius. Above the core is the radiative zone. In this region, the energy produced in the core propagates outward in the form of radiation. However, due to the high density, photons constantly collide with other particles as they radiate outward. As a result, it may take at least 100,000 years for photons to travel from here to the outer layers. Next is the convective zone. In this region, plasma undergoes intense convection, and the temperature generally drops to below 2 million degrees Celsius. Beyond the convective zone lies the photosphere, which is the visible surface of the Sun as seen from Earth, with a temperature of about 5,500 degrees Celsius. Here, the plasma is in a state of boiling motion, continuously rising from the Sun's interior and then cooling and sinking. Above the photosphere is the chromosphere, a thin layer about 2,000 kilometers thick. This layer is filled with hot gas jets, which are the material ejected during solar flares. Finally, there is the corona, the outermost layer of the Sun, with temperatures as high as 2 million degrees Celsius. Corona is only visible during a solar eclipse or through special X-ray images. Why the corona is so hot remains a mystery, and there is no definitive answer yet.